continue finite element. So we already started last time on finite element. So we started on introducing the idea of projection. It is a generalization of projecting a point in 3D space into a 2D space, and we generalize that concept so that we are projecting an infinite dimensional space into a finite dimensional space. We are projecting a function or the residual of a differential equation, which is another function. We project the function into a space of also functions, but with some restrictions. Right? We are projecting the space of any function into a space of piecewise linear and continuous functions last time. So that idea is allowing us to basically stay in the space of functions. Instead of like finite difference or finite element, we only keep some of the information of function. We still work in the space of functions, but now it is a restricted space of functions that can be spanned by a finite number of basis functions. Today we are first going to review that and trying to put this concept into more lights, and then we'll demonstrate how it actually works in practice. And today we are going to do this not only in 1D but also in 2D, so that like we get a sense of what we are talking about better. So first of all, we have a space omega. Let's just say it's a space like that, a two-dimensional space that is omega. All right. And we are solving the Poissons equation. The divergence of the gradient of a field U is equal to F. So that's the Poissons equation we are solving. It's second derivative of U equal to F, right? And we can write the second order derivative as the divergence of the gradient. Fine. With the boundary condition U equal to 0 at the boundary of omega everywhere. Okay. So what we are doing in finite element is we are projecting the residual of this function onto a finite dimensional space, right? Okay, so we are doing two things actually. Let me write down these two things better. So first of all, we are approximating U, we are restricting U so that U has to be in the space of XH. Okay, and let me describe what XH is in this two-dimensional case. So let's say we are discretizing this space into triangles. Okay, I'm just going to do things very closely here. Okay, we have a bunch of triangles that covers the domain. Okay, and this XH is continuous and piecewise linear in this space of triangles. That means in each triangle, on each triangle, the function has to be linear. Okay, do we have a concept of what that function looks like? It's like tens, exactly. So in one dimension, if we fix the value of a function at two different axes, that uniquely defines a linear function, right, within a particular interval. If we define the value of the function at the two ends of the interval, that defines a linear function. In 2D, if we define the value of the function at 3 points that forms a triangle, that uniquely defines a linear function. Right? 3 points defines a unique linear function in 2D. And in 3D, what do we need to uniquely define a linear function? 4 points that would form a tetrahedral exactly. Right. So here, in this case, in 2D, let's think of what that linear function would look like. So let me give a special case. So let's say if we look at this biggest triangle in this domain, and if the value of the function is 1 here and 0 here and 0 here, how would the linear function look like? How would the contour of this linear function look like? Yeah, the contour would look parallel to this line. So it'll be 0 on this line, right? It's a linear function. It's 0 here, 0 here, so linear function means it's 0 along that line. And it's 1 here means the function has to progressively get higher and higher as you go towards that node of 1. So you get a linear set of contours that goes higher and higher towards 1. Okay. Or if, let's take another case, if the same triangle, if I have the linear function to be 1 here, 0 here, 0 here, the contour look like that. And if again, it's 1 here, 0 here, 0 here, the contours would look like that. Okay, now we have these 3 cases. For any value you can define on these 3 points, you can take a linear combination of these 3 functions and obtain the linear function that takes any value at these 3 node points. Right? This is how this continuous and piecewise linear function would look like. And these constructs are also going to help us build a basis later on. Okay, because the basis in 1D would be the function that takes the value of 1 at 1 grid point and 0 for all the other grid points. So we'll take a look at, we will see, we construct a basis exactly like that later on. Okay, so we restrict our solution to be within that space. And the space also has another constraint like we had last time, which takes value 0 at the boundary. Okay, so that means on this boundary, which is in this case discretized as this a collection of linear segments, on this boundary, the value of u, for which u lies within this XH, the finite dimensional space, has to be 0. It has to satisfy the boundary condition. So this is the first thing we do in finite element, is that we restrict the solution into a smaller space, into a finite dimensional space. Okay, what is the second thing we do in finite element? Something we said that is most important. Projection. 2 is we project the residual minus f onto the same space XH. And this XH equal to that XH means the most typical finite element method, the Galerkin method. All right. Okay. So let's take a look at, in this case, what does this projection mean? The projection means the integration of over this whole domain, okay, of the residual times any v has to be equal to 0, right? For any v within the same XH. Okay, I want to remind you what the projection means in the 3D to 2D projection. It means the difference between the 3-dimensional point to the 2-dimensional point. Okay, the difference has to be orthogonal to any vector that lies in the 2-dimensional space. Okay, here what we are saying is that the residual projected on the 2-dimensional space has to be 0, right? So the 2-dimensional projection of this pen is 0. That means the difference between the three-dimensional object to 0, which is actually the 3D space itself, which is this residual, right? This residual is a full function. It doesn't have to be in the 2D space or the finite dimensional space. The residual itself has to be orthogonal to any vector in this finite dimensional space, which is this V. This V is this any vector. The inner product is this integration over the whole domain. Okay. So this has to be 0, which means they have to be orthogonal to each other. Okay, and now we can do something more to this formulation. That is a typical of finite element. That is, we want to perform an integration by parts, so that we remove some of the derivatives on the solution U space and put that derivative into the V space. And the result of that integration by parts, the result of removing some derivative on U and putting some derivative on V, achieves the result that it puts a less requirement on the solution on the solution U. So here, if you look at the differential form, U has to be twice differentiable. But if you can remove one derivative in U, you only require U to be once differentiable, which actually makes this piecewise linear space possible, right? Otherwise, you have to use higher order elements. You have to enforce, that is much more difficult because you need to construct a space that the function is not only continuous, but the derivative has to be continuous so that you can do second order derivatives. Now, this doesn't have to be true because we have the powerful tool of integration by parts. Integration by parts. Integration by parts is an extension of what we used in finite volume. It's an extension of the divergence theorem. Okay. It applies its divergence theorem on the vector field of, let me define a vector field. Let me define the vector field W as the gradient of U times V. Okay, it's a vector because it's a gradient times a scalar. It's a vector times a scalar, right? The divergence theorem says that the integration over this whole domain of the divergence of this W is equal to integration over the boundary of normal